the topic is about opportunities for energy savings in drives. We have, since the last 3 years, had energy efficiency classes for drives, first introduced by the European standard EN 5598, later by IEC 61800-9. There are 3 classes, IE0 to IE2, and preliminary investigations show that all drives are class IE2. And you can see in this graph here, I took 3 of our products, one developed in Denmark, one developed in China, one developed in Finland, and I tried to plot where the losses in the drive are compared to the IE2 limit, and they are far below this. So as Konrad earlier mentioned, it seems to be a problem. But the problem is not clarified yet because we don't know yet what the definition of the complete drive is, what impact filters have, and so on. And there will be some activities in the future to determine what is the solution to this question. But then again, do IE classes make sense? Do we really get more efficiency out of a drive which is 98% efficient by introducing more classes? Well, you see, the answer to this question, in my opinion, I think it lies in the physics of power electronics, because there is a relationship between efficiency and cost. If power electronics is less efficient, it needs more cooling, you will need more heat sink, more fans, it will become more expensive. If a power electronics device is more efficient, that means less losses. You can build it smaller. You can have a smaller heat sink, you can have smaller fans, and at the end of the day, you will get a less costly product. So the physics of the losses has this sort of rule for power electronics, which is different from motors. I'll come back to that. I show you an example here. We recently made a redesign of our high power drives, and I took example something we call the E-frame. It's a 400 kilowatt drive. Before, the old version had 8,600 watt losses. The new version had 8,000 watt losses. So we did this improvement because we wanted to make a smaller size. We wanted to reduce cost. We had approximately 5 to 10% cost reduction, and we achieved this by reducing losses. So the physics of the loss in power electronics is different from the physics of the loss in motors. In order to make a more efficient motor, you need to put more material or more special materials. So that means the cost for a motor increases with a high efficiency. For drives, up to a certain limit, the cost drops. But then you hit a limit. And what is the limit? And I think we are today at that limit. Maybe the hardest limit is the limitation of the DU/dt, of how fast you can switch at the output of the drive, because that DU/dt affects the insulation of the motor. So you can destroy the motor if you switch much faster. There are some possibilities to improve the efficiency of a drive. Of course, we have seen in Konrad's presentation also a slide about falling price of silicon carbide. We all know that. Actually, Danfoss is building a joint venture with General Electric in the state of New York, an entire factory focused on building SiC power modules, but not for motor drives. Yet, because the issue is the very fast switching destroys the motor insulation. The very fast switching means higher electromagnetic interference. So what to do? When you use these high, or let's say fast switching devices with very high efficiency, then you need to add a filter. So what you save on the switching devices, on semiconductors, you almost waste on passive components, which are used to compensate for the secondary effects of the fast switching. So at the end of the day, you don't get so much out of this deal. But then, how to increase efficiency? And I think we have the answer in looking at efficiency at system level. And we had also a presentation this morning where there was said, to quote exactly, it was Mr. Richard Phillips said that with system approach, the efficiency improvements can be increased by a factor 10. And I couldn't agree more. We have in the new drive standard for energy efficiency 61800-9, we have the system where we have the drive and the motor. And if we look at system level, there we can do most of the improvements. But an enabler for this so-called extended product approach is data availability. That means I need to know what the efficiency is of the drive and of the motor, not only at full load. You can see that demonstration over there. I hope all of you saw how the efficiency drops in partial load. It's very important to understand what the efficiency of the components is in part load. For drives, it's not a problem. Most drive manufacturers publish now, or at least the important drive manufacturers publish their efficiency at part load. For motor, it's rather the exception. The motors we have here, the Bauer motors, they are one of the notable exceptions of publishing part load data. But most manufacturers still are not open about this data. And then there is also the issue about in which format should we present the data. You can use the format from EN5598 with 8 part load points, or you can use the format with 7 part load points from IC 60034 motor standard. So there are two formats. They are mutually interchangeable. And our experience shows that the IC standard gives better results, but we need the data, no matter in what format. So that's an important enabler for system-level optimization. Then, if you look at the drive only, the efficiency of the drive, that says something about the power electronics, but what we don't see by the IE class is the impact the control algorithm of the drive has on the system efficiency. And I will give you two examples here. One example is for induction motor, shown here. The induction motor drops, the induction motor efficiency drops at lower loads. That is what you can see with a blue curve up there. But then the control can use something called automatic energy optimization. That's what we call it in Danfoss. But most other competitors also have a similar function. It's about optimizing the magnetization flux depending on load. And by doing that relatively simple thing, the efficiency increases a lot at partial load. Of course, at full load, you need full magnetization. That's not in discussion. But at part load, there is a very, very, very large potential. And we can squeeze more efficiency out of the, let's say, all-day induction motors. For permanent, or in general for synchronous motors, the preferred control strategy is something called maximum torque per amp. That means let's get as much torque as we can out of a certain current. It's important to say that in order to determine the maximum torque per amp curve, the drive needs to be matched with a motor or to be able to identify the advanced motor parameters. That's one thing. The other thing, maximum torque per amp doesn't mean maximum efficiency of the motor. But current causes losses in the drive. So at system level, if you look, maximum torque per amp is as close to maximum efficiency as you could get in practical terms. Then I would like to finish by saying a couple of words about future trends. One of them, a trend we are seeing, is more focus on life cycle cost, more focus on total cost of ownership. We had previously a presentation which mentioned life cycle costs. We can see that we have customers who send requests for quotes where we need to provide information about the life cycle cost. So this is important, and this makes the system level approach even more important, because we cannot answer to life cycle costs by looking only at the components and thinking only in terms of classification. Then digitalization, that's a major revolution. Industrial Internet of Things, as we heard also this morning, this is the big revolution which will change much more than a simple classification. And I have an example here, but we also heard an example earlier today. This example here is a pump. You take a nice, highly efficient pump, but in time the efficiency of the pump is dropping because of sludge, because of wear out, because of fouling, and so on. If you are able to monitor this with a condition monitoring system, condition monitoring of the pump, then you are able to perform some maintenance to clean the pump before you get so down that you observe or the maintenance guy sees it without measuring. We have seen this morning also a presentation from a chocolate factory with a fan, where the fan was cleaned when making the upgrade of the system. So the motor was changed. That was one initiative. The other initiative was frequency converter updated, and then another initiative was cleaning of the fan. It's again, that's something that can be done by condition monitoring. The drive itself, the drive as a sensor, can detect such a condition and can signal the necessity of maintenance. Thank you very much. I have questions?